Hi, everyone. Thanks for coming to our presentation. I was going to be presenting today with Spencer Gibb. Unfortunately, due to an unforeseen emergency, he will not be able to join us today. However, we worked on this presentation together and also on all the code that is in the demos, so we should be able to get it done. So let's talk about resilient and adaptable systems and about cloud-native APIs. We will discuss what the cloud-native API is. We will talk about the protocols that are used and what is new and interesting. We will talk about the gateways, about architecture, and I will show a demo that has some well-known Spring Cloud tools in it, but also has some really new things. So first we want to discuss the question, really, what is a cloud-native API? In today's world, cloud-native APIs really mean API first. The API is the product. Customers may interact with your product in various ways: mobile apps, web apps, IoT devices. In some cases, like Stripe, which is a payments API company, or Twilio, which is an API for text messaging, the API literally is the product, but of course not in all cases. Even products without public APIs have private or internal ones. While you might not interact with a public API from streaming services, big box retailers, shipping companies, or VMware, rest assured that they are all thinking and writing API first. Cloud-native APIs are composed by cloud-native systems, not just cloud-native apps, individual instances, networks, or load balancers, but all those pieces together acting cohesively are, in fact, the API. All the characteristics of a cloud-native application bubble up to the API, such as resilience, fault tolerance, and rate limiting. Rather than applying to individual services, these attributes are now part of the API. And that makes the API greater than some of its parts. And another trend that we see a lot these days is serverless. I really like this definition by Mike Roberts, which says that serverless is server-side architecture run in stateless, event-triggered, ephemeral compute containers. There are two most popular approaches to serverless that we see. First one is backend as a service, and there we have a lot of logic run on the client side and data taken from various backend services, often on a subscription basis. And the other one is function as a service. Here, we encapsulate the business logic in single functions, which are then run in containers, which are usually spawned as we get an event requesting some data that the function calculates, for example. And very often, later on, these containers are stopped after doing just that. It's very important that they're event-driven, and they have a lot of advantages. Mostly the fact that the infrastructure is handled by cloud providers, so we don't need to worry about things like capacity, provisioning, and patching. Also, with this model, we get automated scaling, built-in high availability, which is at the center of this approach, and also a pay-for-use billing model. So we only pay for whatever time or memory that we use when this container is running. And this, of course, gives us enormous flexibility. And this also brings along the emphasis on short startup time and low memory footprint. When we think about optimizing our applications, there are various things that we can optimize for. So just up until a few years ago, we mostly tried to optimize for peak throughput and reduced maximum latency. But when we think about serverless applications, very often what we will instead try to optimize for is short startup time and low memory footprint. And this is because we pay for the time and we pay for the memory that our containers are being used. So because of this, we see trends such as using GraalVM native Java images gaining popularity, because they will allow us to run our applications really fast. And they will also allow us to use very little memory. And in Spring, in order to meet these needs, we have created the Spring Native Initiative, which provides support for native GraalVM-based images for Spring applications. And it also now provides an AOT plugin that basically runs through your code during build time and rewrites parts of your code to make them more optimized, specifically the Spring configurations, which are heavy in reflection, but thanks to the use of AOT plugin, it is going to be optimized for you. Of course, as any approach, serverless will also have its drawbacks. So we have definitely a higher system complexity. Yeah, if we only have like a coordination of, let's say, various functions as a service that we are running in different places. And then we also can have higher monitoring and tracing complexity. And we might also be at risk of vendor locks if we don't watch out and we adjust too much to certain vendor tools and approaches. And there's also one other interesting thing. So actually just recently, I was listening to Neil Ford at Devoxx Poland, and he mentioned that he thought serverless might also be at the risk of what is called the last 10% trap, where 80% of things that you might want to do are very easy to get done. 10% are difficult, but still possible. But there also exists a 10% of things that are just impossible to implement. So it's possibly too early to say if things really will go this way, but we might want to keep it in mind and possibly have systems that have some function as a service use, but are not always entirely comprised of this, depending on the use case. When it comes to support for serverless and serverless functions, we have a project in Spring Cloud called Spring Cloud Function that allows you to register your functions as beans in this very simple way that you see in the slide. And it allows you to implement your business logic via those functions. And what is also great is that it provides support for Spring Boot features on serverless providers. And what I think is actually most important is that it provides a single additional layer of abstraction so that it works across different serverless providers, and you have another layer of abstraction protecting you from vendor locks. Also, 1 month ago, VMware has announced the Tanzu application platform, which allows for easier building, deploying, and operating applications in Kubernetes-based ecosystems. Next, we'll talk a bit about efficiency and speed. When we think about today's cloud-native applications and we think about responsiveness, it is not only important just as in a responsive web app, but also in the sense of responding to changes in the environment and in the network, and its ability to optimize for availability and speed. It is also about protocols. The web is initially built on text-based protocols, but modern APIs can use binary protocols, and in this way they can gain some efficiency and speed. Also, infrastructure is important. Scaling and resiliency definitely have an impact on our APIs, and whether your infrastructure is just straight on-prem, serverless, or made in a different way, arranged in a different, over different infrastructure, will impact the ways that your applications communicate with each other. And then we have the Spring ecosystem that will allow you to focus on your core business and take over a lot of the work that is repeated and would have to be redone and re-implemented for different applications to make them run seamlessly in a cloud-native environment. Another thing to keep in mind about the cloud-native APIs these days is that now they're very often evolving. It is now something that we can see as a usual approach in microservice-based ecosystems. And in fact, it makes a lot of sense because now intra-service communication has become part of the functionalities implementation. It's not even only part of it, it's at the center of our systems usually. So obviously, if we want to change or broaden or just develop further our implementation and add more features, and we have this communication layer which is at the core of the system, we need to be able to evolve the APIs, and we need to be able to evolve the ways that different components of our systems will communicate with each other. Also, it is now possible to do it because a lot of these APIs that we are talking about are internal ones. So not only public APIs that are on the edge and that are difficult, more difficult to evolve or slower and usually require rigid versioning. We also have a lot of APIs built within our systems that our teams control and where we are much more flexible when it comes to evolving and changing them. However, if we are going to do this, so to evolve APIs, we need to put a lot of attention on backwards compatibility. That is because in a microservice-based ecosystems, we need to be able to decouple our deployments. So not only development and services, but the deployment. We need to be able to deploy any of the services independently, and we cannot really allow for a situation where, in order to achieve compatibility with a newer API version, we will also need to upgrade and deploy a bunch of other services that communicate through it. This is not something which should be done. So we need to use different approaches to address this situation. I have put here 3 that are often used. One is addition only. So with this approach, we don't really ever remove anything from the API and only add. Another one is tolerant consumers. In this approach, the parties that read the APIs read the responses that they get from the APIs, but only really take into account the data that matters to them. So it is a scenario-based approach and not a schema one. The services do not care if something is changed in the response fields that they do not use for their business functionalities. They do not care if there's any other service that uses or does not use those fields. And then there are deferred updates, which is an approach that is also present in database engineering. And basically what we want to do here is first just to add something new to our API, then wait until all our clients or all the services that communicate with us have adjusted to using this new feature, and then only we can remove the deprecated element. So in order to make this kind of evolving APIs safe, we need to be able to ensure that our integration does not break. And it has now become a key concern to us. And this, in turn, has led to the increased popularity of consumer-driven contracts, where the parties, so the clients and the producers of an API, define a contract that specifies what exactly the API should look like. And the core feature here is that there has to be a mechanism in place that ensures that the actual API on the producer side really meets this contract. It is a collaborative approach, so both parties work together on the API. It is, again, usually scenario-based and not schema-based. And it also has to provide fast integration tests for consumers. And one other thing that it provides is exactly testing for backwards compatibility. Because when we then write new code and we have a newer version of our API and some new code, and we put it in our deployment pipeline, and in one step, we will test it against the new contract. So we updated the API, but we have also updated the contract. But we will also test it against the previous version of the contract. And if it passes, then we can be sure that actually the changes are still backwards compatible. So in Spring Cloud, we have this Spring Cloud contract project, which is exactly a consumer-driven contracts approach implementation. And we create contracts. As you can see in the slide, the way we do it is quite intuitive because we just stick with the known HTTP call conventions. So we have requests, responses, methods, etc. And this kind of contract, if you add it, and if you add obviously appropriate plugins to your setup, will provide you either wire mock.json stubs if you are using HTTP, or mocked messaging route setup for messaging for consumer integration tests on one side. And on the other side, it will generate tests for you that will automatically verify that your actual producer code, so your actual API, meets the contract. If it doesn't, the build will fail. So in this way, it provides fast but also reliable reliable tests for producer side and consumer side. And we've already done a lot of detailed presentations on Spring Cloud contracts, and I even did a presentation on it here at JDD some years ago. So if you're interested in that, you can go and check it out. I will not go more into details, but it is really an interesting approach if you are evolving your APIs. Our APIs in distributed systems are built upon some kind of wire protocols. So we're going to talk about some of those and how they fit into this cloud native API ecosystem. The first one that comes to mind, the one that everyone has seen, used, etc., is of course HTTP. As we know, HTTP is actually document-based, resource-oriented protocol. It was created with simple CRUD operations in thought. So creating resources, updating resources, deleting resources, etc. But it is also very, very easy, simple, and straightforward, which is probably why step by step and over the time, it has started to be used in scenarios which are way more complex than just simple CRUD operations. And even in use cases that really go very far beyond that resource-oriented approach. This, of course, has started to pose a series of issues because the protocol has not been created with the kind of scenarios in thought that are actually being carried out right now. So, first of all, we have head of line blocking, which means that only one request outstanding on a connection at a time can be there, with HTTP1 anyway. Then we have this client-server or request-response approach, where an interaction always needs to be initiated by the clients. So a lot of times we'll have situations where our clients will just keep polling the service just to check if anything has changed, because there is no easy push mechanism where the server can just inform us of some changes. It is also synchronous, and because it is typically TCP-based, there is a lot of handshake overhead for every connection. And as there is the head of line blocking problem, we usually also have many connections open, which is not very efficient. Also, important thing to keep in mind, I really like this quote by Rutger Millet that I have actually first heard at the presentation of Tomek Nurkiewicz, which says that the internet is running in debug mode. So yeah, we go on sending these nice text JSONs, and they're awesome. They're very easy for us to read and debug. However, they're not necessarily the best way for machines to communicate, and definitely not the most efficient one. So HTTP2 is trying to address a lot of these issues. It is a binary protocol. It is also a multiplex protocol, so it allows for parallel requests to be handled over the same connection. And it removes the order and the blocking constraints from the HTTP1 protocol. It also offers some header compression and some kind of push mechanism based on client caching. So it is still not the ideal thing, but definitely a step in the good direction. And the upcoming HTTP3 is actually quite exciting because it is planned to be made based on QUIC, and QUIC as a multiplex transport that is built on top of UDP. So it will have much less overhead at the beginning of every connection. Message-based protocols are increasingly important in the cloud-native landscape These allow other interaction models beyond just the request response. And message brokers such as RabbitMQ or Kafka offer this distributed messaging and streaming semantics that are super interesting. They allow different interaction models such as topics and queues. Topics are one-to-many, so one message can be seen by many consumers, while queues, which are one message, where one message gets seen by one consumer. So depending on the needs of your application, you can pick between these different kinds of interaction models. Messages can also be either durable or ephemeral. Durable means that the message is persisted to some kind of storage device, and this allows for high availability and resiliency. Consumers can come back and read those messages, even if there are some kind of network failures. Messaging also allows for separation of concerns at the API level. That means that consumers who are interested in a particular set of data can just listen for the appropriate messages. There doesn't have to be tight coupling between services in our microservice architectures. And architectures such as event sourcing and command query responsibility segregation, or as most of you probably know, it's CQRS, depend heavily on these message systems. Another protocol, which is quite fresh and new, but we think is really interesting, is RSocket. So what RSocket actually does is to take the reactive stream semantics that, again, I guess many of you are familiar with, take them onto the protocol level. So with reactive streams, we see the responses that we're getting as streams of events, streams of data that we can later filter, map, handle error streams, and so on. And one other very important thing here is also this so-called back pressure, so that the subscriber can request an n number of events or elements of the stream, and therefore there is no congestion. So all these concepts are being used by RSocket. The RSocket protocol models all communication as multiplex streams of messages over a single connection. And that's why it never synchronously blocks while waiting for a response. So it is message-driven and fully asynchronous. What is super interesting is also the fact that it has various modes of operating. So we do not have anymore only request response, because let's face it, our scenarios often require very different interaction models. So we also have fire and forget, where we just send something and we do not really care about a response. Then we have, of course, the traditional request and response. But we can also have a request with a stream response, where we expect to get a stream of elements or events in our response and not just one. And then we also have the bidirectional channel, where both parties can just communicate in whichever order they like. It also has inbuilt flow control. So first of all, we have this back pressure mechanism, which works exactly like with reactive streams. So you can just request a number of elements only. And it also has leasing, which is a way for the servers to signal their capacity. And this is something that is very handy, for example, with load balancing. This protocol is binary, and it can work over a variety of transports. So we have TCP, but we also have WebSockets, Aaron, which is UDP-built transport, and there are also plans to support HTTP3 and QUIC in the future. After we've seen the protocols, we'll talk a bit about gateways and how they are part of this cloud-native landscape and the cloud-native APIs, and how important they are, especially with regards to protocols and stitching our APIs together. But first, there is an important aspect that we need to talk about before we get directly to gateways. This aspect is discoverability. So before, some time ago, we could just assume that we could hardcore our hosts and pods and just be happy about knowing where the applications are running. And even though already many years ago it was considered as one of the fallacies of distributed computing to assume that the network topology doesn't change, now this process has sped up a lot. So now the change in topology is constant. We have those serverless containers coming up and going down. We have Kubernetes containers being created one by one and then destroyed. We have many instances of every service running in various clouds. So we cannot anymore rely on the client knowing where the server instances are. So a popular approach to solve this problem has been service registration and discovery, where we use a service registry where all the services register their instances, and the service registry also has knowledge about the health state of these instances. So then, when a service wants to connect to another one, let's say the service B wants to send a request to the service A, it will first query the service registry for the instances of the service A. And then once it knows what the healthy instances are, and usually once it has selected the instance using some kind of client-side load balancing mechanism, it sends a request and gets a response. So the first gateway I would like to talk about is Spring Cloud Gateway. Spring Cloud Gateway is a developer-friendly API gateway, and when we built it, we focused on the developer experience. So Spring Cloud Gateway is just a Spring Boot application. We want to say deployments and not tickets, and it is not just your old ESB. Spring Cloud Gateway, in fact, is the glue for your HTTP-based APIs. You connect different microservices to act as a cohesive API, and it doesn't really matter what your clients are on the other side because they only interact with Gateway, whether they are a mobile app or a web app. Gateway is a place where you can apply cross-cutting concerns to all the services that make up your API. It allows a single place to secure your system. Complex things like rate limiting can happen in the Spring Cloud Gateway. Fault tolerance, so things like retries and circuit breakers can happen at one place in Spring Cloud Gateway, and obviously something simple like load balancing, where you pick between instances of a particular service. Another tool that we want to talk a bit about is the RSocket Broker, which is a specialized message broker for the RSocket protocol. And this, again, is an interesting solution where you can apply security and fault tolerance at one point for all your system. The fault tolerance is handled a little bit differently here than as opposed to the Spring Cloud Gateway, because the RSocket protocol itself has things built in, and load balancing can happen in the centralized broker. And we will also see how service discovery works when we show a diagram. So RSocket Broker works by having a small cluster of broker instances. And in this particular diagram, we can see 3 of them. And as the services come up, they register directly to the broker when they connect. And each broker node communicates with the cluster. And you get a full picture of all the services that are connected. And so the broker becomes the de facto service discovery mechanism. And interestingly, for security, these services can actually block all the incoming connections, because all the incoming requests, in fact, come over the outbound connections that these services already made to the RSocket broker. So they're extremely secure, since no one can make any new connections to those services. Load balancing is done as a service makes a request. It will pass a little bit of metadata called tags to the broker, and then the broker can select the appropriate service instance or a subset of instances that the request should go to. So the broker allows for additional interaction models, such as broadcasting messages, as opposed to just single instance messaging. What's also interesting here is that Spring Cloud function that we've talked about has RSocket integration. And with that, if you need durable messages, you could also send those messages through RSocket to Kafka or RabbitMQ. And in the Spring team and in the Spring Cloud team, we actually talk quite a lot about RSocket and about RSocket routing broker, because we think this protocol is super interesting and it's a great technology. However, we also do realize that a lot of people just have these systems that are already built on top of different protocols, and that is usually impossible to just change the system overnight. Of course, what we usually do in these kind of situations is to create some kind of adapter through which our systems can communicate. So we can have some parts using a different protocol, and then we have parts using a newer solution, such as RSocket, and we use the adapter to make that communication possible. Obviously, this can be built by anybody, but we decided that as we want to popularize RSocket more and more, we were going to make it easier for everyone. And just around 3 months ago, we developed the RSocket HTTP bridge that does just that. And this is something that we will see in the demo shortly. So the bridge is actually just a small dependency. It is a module in the RSocket routing broker. It is built on top of Spring Cloud function, and it allows you to do HTTP posts to the bridge, where you will just specify your service ID. And then you will specify your RSocket endpoint. Actually, this form of calling a request with a certain service ID is very similar to the way that the Spring Cloud's HTTP stack works. For example, with service discovery, load balancing, and so on. So here it works similarly. You just pass this information, and then you pass your payload. For example, you send some kind of JSON, because that's what your services are talking in if you're going to be using the HTTP bridge. And then you can also pass additional information, so you can pass some tags as headers. And what the bridge will do, it just take all this information to connect to the broker and send a payload through the broker to the end service. The HTTP method that we support is post, and we support byte arrays as our content type. We also allow passing tags as headers, as I said, and you can also specify the interaction mode in the URI as the first segment. So, for example, fire and forget or request response. And if you do not specify it, our default will be used, which is request response, but you can also specify your own default for all the communication. We also handle well-known keys, which might be an interesting bit of information for those of you that already use RSocket routing, client, and broker. The well-known keys are basically a predefined way of specifying certain information that allows you to choose the right instance, such as, for example, the instance ID. So now that we've talked about all these different protocols and gateways and things that can make up your cloud native APIs, we are going to talk a little bit about architecture. There are typically two kinds. So first up is greenfield. What greenfield means is that there is no existing applications. It's all new. This is really exciting for builders because it allows us to pick the right tool for the job. Our restrictions aren't based on an existing technology, but on other factors, and they can vary widely across organizations. It could be budget, it could be personnel, so who you have on teams or who you plan to hire on teams, how quickly you want to get this thing to market, and what the requirements are. And it allows a freedom of choice. So you can choose your platform or container service. You can get to choose programming languages, and actually the gateways and the protocols like our RSocket that we've just talked about are all language independent. You can pick the protocols that you need, whether that's RSocket or you need HTTP or maybe some other binary protocol or messaging using RabbitMQ or Kafka. And the world is great. But we all know that life is not always that great. And we don't always just get greenfield projects where we can do whatever we want. Very often we work with legacy or often also so-called heritage systems, which tend to be old, big, with quite a lot of technical debt. However, they're also very important because they're often vital for our businesses. So they are the core point of our systems and our business functionalities, and they really allow us to serve our customers. So they're also very good in this way. And very often we cannot just throw them and start building something new. But what we would like to do, because we want to have this functionality running all the time, but we don't necessarily want to keep acquiring technical debt. So what we want to do is being able to start changing them slowly and adapt them. So very often what is done is modernizing such architecture by areas or components. Like say we have a monolith. We will often start by thinking about what our bounded contexts are in this monolith, and then maybe divide it into modules until it becomes a monolith. And then maybe we want to be able to scale some of these modules horizontally. So we will actually turn them into separate microservices. And we can imagine that we have this kind of a legacy service and then a newer part of our ecosystem which uses RSocket to communicate and has the RSocket Broker at its heart. And we would like to make it work together. This is a kind of situation exactly where we will use the HTTP RSocket bridge or any other adapter you could use, you could have built on your own basically, but we just thought it would be useful if we provided one already ready-made. And this is a kind of approach that we will be trying to showcase in the demo. And in the demo, we will see a loan service where people are trying to apply to get a loan. And that service has to be, and that service actually HTTP based and wants to communicate with a new RSocket based verification service to check if a customer is fine. So basically in our simple use case, if the customer is old enough. And then we will have the RSocket Broker and we will have the RSocket verification service instance running. And we will have the Spring Cloud Gateway, but it will not be a regular Spring Cloud Gateway instance. It will be one that will also be an HTTP RSocket bridge at the same time. And we will be sending these requests from the loan service through that gateway / RSocket HTTP bridge to the RSocket Broker, and then passing them on to get a response from the verification service, and then all the way back. So let's see some code. Okay, I have this project running here, and let's first start with our loan service. So we can see the POM. It's just a simple HTTP-based application. We are using Webflux for our communication, and we also have a Spring Cloud starter, so we can use, for example, service discovery. And we will have a controller. So this is our start point of our flow. We'll be able to make requests here, and then we'll be using this verification service client underneath. And as we see, that client will be using discovery client to find the instances of gateway that could obviously be load balanced as well. I just wanted to show you some more details. And once it finds an instance, it will be passing a request that we can see here. So it will go through that gateway, then to the RSocket Broker, and then to the other service. And you can also see that here we are actually checking for an instance ID in properties. And if we do find it, we add a header, which is XRSocket tags, so that's the header name, but this is also customizable. And then we actually add one of these so-called well-known keys, in this case, instance name, and pass the instance ID if we get it in properties. And let's also see our application setup. We're using here simple discovery client. So we usually suggest using actual service registry, but if you want to test something quickly or you're doing some demo like here, there is actually an inbuilt solution where you can just pass the data of your instance, like you can see in the code directly in your properties or in your YAML, and Spring Cloud will just support it out of the box and will find the instance for you. And here we have these profiles. So depending on the profile, we might be adding this instance ID. So the other service that we will have running is going to be the broker application. And this is our RSocket Broker. So we are adding this dependency, RSocket Routing Broker Spring. And to provide integration with RSocket, we use Spring Boot Starter RSocket. And we can see here also our application YAML. So there is some data that we need to pass to make the routing broker work. We always have a broker ID. It is hard-coded here for the demo, but it can also be just assigned by the broker by default. And we also need to set up some connection data. So we can see here the TCP setup. In this case, TCP is our default, and that's what we'll be using in this demo. And actually, I have one instance running, but there could be more. We also have our verification service. So this is our client, RSocket client, and we are using RSocket Routing Client Spring dependency, and then also Spring Boot Starter RSocket to allow for the RSocket integration. And we can see our application setup. As you can see, we are using this. We have put the service name, which is a well-known key and which is the only required well-known key. And then we have also added additional tags, which are optional. In this case, I am putting the instance name. So here I have one instance name, and here, if I run it with a different profile, I have another. And then this verification service, as we can see here, uses the controller annotation. And what Spring RSocket integration provides is that now we can use the message mapping annotation also to handle RSocket requests, not only the regular traditional messages. So that's what we are doing. We are getting an RSocket request, processing it. Some logic is implemented. Basically, just we check if our customer that we have passed is old enough, and then we return some response. And the last bit is our gateway. So this gateway application has, of course, the Spring Cloud Starter Gateway, but it also has this RSocket Routing HTTP Bridge dependency. And it will convert it in the HTTP Bridge app. Obviously, you don't need the gateway for this. You could have a separate app, but we assume anyway, it's good to have this gateway for your HTTP communication for all sorts of it. And you don't need a separate app just to handle your connections that go from HTTP to RSocket services. You can use the gateway as well. And in order to do this, you need some setup, which is going to be super simple. So usually in gateway, you will have routes to define how all the connections are going to be handled. And usually you would have many more of them, but I have added only the one to go to the RSocket bridge. So we are going to just forward whichever request comes at the verify path, we're going to forward to verification service verify. And this will be resolved to the service ID of the RSocket app that will be passed to the broker and then to the actual endpoint. So we have also a JSON, okay, with some correct customer and one with some incorrect customer. Now, if we run the request, we see it passes. So that goes through all the flow. You can later download the demo. It's in GitHub and just play with it on your own. And now I'm also going to show you a request that will go directly to that gateway. So that is running on port 9081. And I'm passing this header to say that I'm only interested in this one instance to send me a response and not any other. And to show you that it actually works, I have this instance running here. So I have passed here a profile. And this one has a different instance ID, the one that we actually need here. And we can also see that everything is being logged here. So I'm going to kill this one. And then if I request it to send me a response just from this one, it will not work. So it will basically time out. That depends on our timeout settings that we have for HTTP connections. But yes, you can pass more tags. Also, region, version, whatever well-known keys are handled to get your requests served by the instances that you want it to be served by. And that is all the presentation. I hope you found something interesting. I'm leaving the links to the demo. Only one thing to keep in mind is that this bridge is still in a snapshot version, so you might need to build it on your own. Once we release that version, you will, of course, not have to do this anymore. And then also there are links to all the projects that I have mentioned here and to RSocket, which is awesome. Please try RSocket. And thank you very much. Let's go back to the studio.